Howdy, welcome. So in this video, I'm just gonna quick go through a couple questions that you asked me about. So again, these are in chapter 4. I'm gonna apologize. My numbers are probably a little bit different than yours, but the type of question is the same. So hopefully, this will kind of help you figure those out. In the future, I think that I can actually get to your questions, so I can actually use your numbers, but I forgot about that this time around. So in the future, it's probably be a little bit more helpful. But again, hopefully this kind of gives you an idea, and you can just kind of plug in your appropriate numbers there. All right, so the first one you asked about was question 9. So question 9 says, a ball rolls onto the path of your car as you drive down a quiet neighborhood street. So to avoid hitting the child that runs to retrieve the ball, you apply your brakes for 1.4 seconds. The car slows down from 15 meters per second to 9 meters per second, and the mass of the car is 1,110 kilograms. All right. So the first question it asks us to find is the average force exerted on the car. All right. So again, force is equal to mass times acceleration. All right. Okay. So you have force equals mass times acceleration. We're given the mass of the car, so that's the 1,110 kilograms. But we need to find the acceleration. All right, so again, if you recall from the first unit here, the first section, the acceleration is equal to the change in velocity divided by the change in time. So in this case, I know the change in time, so the time over which that force is being applied is 1.4 seconds. And then my change in velocity, so I'm slowing down from 15 meters per second to 9 meters per second. So again, the change in velocity is going to be your final velocity. So in this case, it's going to be 9 minus 15. So we have the final velocity minus the initial velocity there. All right, why is this not focusing? All right. All right. So if you take 9 minus 15, we get negative 6 divided by 1.4. We end up with something around negative 4.28. So negative 4. I'll probably round to 2 decimal places here. So 4.29 it looks like. And this is in meters per second squared. All right, so again, it's negative because we're slowing down. All right. So then to find the force, again, you're just going to take the mass, which again is the mass of the vehicle, which I think in my question was 1,110, times your acceleration, which was 4.29. So you have 1,110 times 4.29. So you end up with negative 4,761.9 newtons. All right. So again, the first part I think is just asking for the magnitude. So you're just going to put in the number there. And then since it's negative, the force is moving, being applied backwards. So it's opposite of your current motion there. So I think the options were either forward or backwards there. So in this case, it's being applied backwards there. All right. So the next one's asked, how far in meters did the car move while braking? All right. So here again from the first couple of chapters, we have that the average velocity is equal to the change in your displacement divided by your change in time. All right. So in this case, we're acting entirely in a single direction. So the change in the displacement is just going to be the change in my distance in this case there. All right. So again, the average velocity is what you get when you take your final velocity plus your initial velocity. So we have 15 plus 9. I think those should actually be flipped around if we're doing final velocity and initial velocity. But again, we're adding. The order in which we add doesn't matter. So whatever. All right, so yeah, so you're gonna take your velocities, add them together, and then divide by 2. So yeah, so when we take 15 plus 9, we end up with 24. When we divide that by 2, we end up with 12 meters per second for my average velocity there. All right, and again, I know that the time that it takes is 1.4. I'm given that in the question. So yeah, so the change in distance is just going to be your average velocity times your change in time, which is going to be 12 times 1.4. So I end up with 16.8 meters. All right. So the next one you mentioned was question 10. Yeah. My scroll doesn't really work very well on this computer mouse. All right. So yeah, so question 10, so we have 2 horizontal forces, P and Q, are acting on a block that is placed on a table. We know that P is directed to the left, but the direction of Q is unknown. It could either be directed to the right or to the left. The object moves along the x-axis. Assume there's no friction. So the net force is just going to be these 2 forces. So yeah, so here P is negative 4.2 newtons, and the mass of the block is 5 kilograms. All right. So yeah, so P is acting 4.2 newtons this way, and the mass of the block is 5 kilograms. All right. So yeah, so question A says, what is the magnitude and direction of Q when the block moves with a constant velocity? All right, so if you have a constant velocity, that means that your acceleration is going to be 0. And if your acceleration is 0, again, your net force is going to be your mass times your acceleration. So in this case, we have our mass times 0, so our net force is going to be 0. So yeah, so in this case, we have our net force is going to equal 0, which again, the only 2 forces we have acting on this block are P and Q. So that means P plus Q is going to equal 0, which again, P is 4.2 newtons to the left, so that's a negative. So we have negative 4.2 plus my first Q equals 0. So then to get Q by itself here, this is just doing some algebra. So you add 4.2 to each side, so you end up with Q equals 4.2, and this is positive 4.2 newtons. Are you gonna focus? No? Okay. There we go. All right, so yeah, so in this case, when you have constant velocity, again, no acceleration, your forces are going to cancel each other out. So if you have a 4.2 Newton force going this way, we also have to have a 4.2 Newton force going that way. All right. So yeah, so the next one says, what is the magnitude and direction of Q when the acceleration of the block is positive 5.5 meters per second? All right, so again, we have our net force is going to equal mass times acceleration. So in this case, my mass is 5 kilograms, and my acceleration is positive 5.5 meters per second squared. So yeah, so in this case, my net force is going to be 5 times 5.5. So we have 27.5. All right, now again, that's my net force. So again, that's what I get when I add up all the forces together. And again, in this case, the only forces that are acting on it are P and Q. So you have P plus Q is equal to 27.5. And again, P is negative 4.2 plus Q equals 27.5. So again, doing the exact same algebra that we did previously, we're just going to add 4.2 to each side. So yeah, so that's going to end up getting me 31.7. And again, this is positive here. So Q equals positive 31.7 newtons. All right, so the final one here is, again, it's going to be kind of the same process. Numbers are going to be slightly different. So yeah, so here we have find the magnitude and direction of Q when the acceleration of the block is negative 5.5 meters per second squared. So yeah, so again, we have our F net is going to be mass times acceleration, which is going to be 5 times negative 5.5, which is going to be negative 27.5 newtons. And again, that's my net force. So again, that's what I get when I add all the forces together. Again, we just have the two forces. So we have P plus Q equals negative 27.5 newtons. Which again, P is negative 4.2 plus Q equals negative 27.5. So again, we're going to add 4.2 to each side. So we have Q equals, so that would end up being 23.3 newtons. And it would end up being negative 23.3 newtons. There. Since 27.5 is bigger than 4.2. All right. All right, so the next one here is looking at pretty much kind of how our muscles work, again, from a relatively quote-unquote elementary standpoint. There's a lot more at play than just this, but for our purposes, we'll kind of run with this there. All right, so yeah, so two muscles in the back of the leg pull upward on the Achilles tendon, as shown in the figure below. These muscles are called the medial and lateral heads of the gastrocnemius muscle. So yeah, so layman's term, calf muscle. All right, so yeah, so we have F2 is 195 newtons, 28 degrees, I guess, west of north, and F1 is 195 newtons, 28 degrees east of north. All right, so yeah, so in this case, when we look at the components of these forces, so yeah, so that's kind of where, so yeah, so there's going to be a vertical and horizontal components to each of these forces here. But the nice thing is, since they're both acting with the same magnitude in opposite directions, the horizontal components are going to end up canceling out. So we really just have to worry about the vertical components. So yeah, so here we're going to have a horizontal component going this way and a horizontal component going this way, but they're going to be the same and they're going in opposite directions, so those are going to end up canceling themselves out. So yeah, so we really just have to worry about the vertical components of my forces here. All right. So in this case, since my angle is with respect to the y-axis, to find the vertical component, so I'm looking for this guy. So that's the side adjacent to my angle. This is my right triangle. And then we have my force is the hypotenuse. So adjacent to the hypotenuse means we're going to use the cosine. So yeah, so F1y is going to be 195 times the cosine of 28 degrees. So I end up with 172.17. Right? And it's going to be the same thing for F2 here. So yeah, so in this case, again, in the vertical direction, they're both acting in the same direction, so it's just going to be double this force here. So yeah, so F2y is also going to be 195 cosine of 28 degrees, since again, the magnitude is the same and the angle is the same here. So yeah, so then the net force is going to be just double that. So 172.17 plus 172.17 is going to be 344.34 newtons. And that's going to be my magnitude. And again, the direction of this force is just going to be net straight up and down. So in this case, it's going to be 0 degrees from the center line. All right. So yeah, so in this case, again, the force is going upward. So that's going to move up. So that's going to raise the heel of the foot. So yeah, so you're kind of standing on your tippy toes. That's kind of what's happening. Again, from a relatively elementary standpoint, again, there's a lot more at play, and I recognize that. But when you boil it down to kind of just the basics, that's kind of what's happening there. All right. So the last one you had for this batch here is you have a skier speeds down a smooth ski slope. Say that 5 times fast. Ew. All right. A skier speeds down a smooth ski slope, which is set at an angle of 17 degrees with the horizontal. So yeah, so you have our skier here. You have a little scarf. We have 17 degrees. All right. The mass of the skier is 75 kilograms. All right. Okay. So yeah, so in this case, force of gravity is a force that moves towards the surface. So in this case, this is my force of gravity, which is mass times the acceleration due to gravity. So yeah, so in this case, we have kind of two components. So one component is what's known as the normal force. So that's the force acting perpendicular to the slant here. We're not really worried about that. We're mainly worried about this force here. All right, so this force, you can go through, you can make similar triangles and work with some right triangles and different things along those lines. But in a nutshell, you get this force is equal to mg times the sine of your angle. All right. And that's, again, kind of the main force that we're worried about there. All right. So our force is equal to a mass, which is 75, times g, which is 9.8. Times the sine of 17 degrees. So 75 times 9.8 times the sine of 17 degrees. So we have the magnitude is going to be 214.89, it looks like, newtons. And yeah, you're going downhill. So yeah, so the direction is going to be positive here. So yeah, so it's a little bit different from kind of what we're used to, where down is generally negative. But in this case, it says take the downhill direction to be positive. So yeah, so in this case, your force is going to be positive there. All right. So again, force equals mass times acceleration. So here we have the force is 214.89. We know the mass is 75. So yeah, so we have 214.89 divided by 75. We're going to put the acceleration of 2.87, it looks like. Meters per second squared. All right. So yeah, so the final question says, how does the net force experienced by a skier change if the ski slope becomes steeper? So yeah, so if your ski slope, still can't say that. So if your ski slope becomes steeper, that means that you're going to be going faster and accelerating faster. So that means that your net force is going to increase. And again, you can tell that by looking at the equations here. So yeah, so the thing that's changing as your ski slope becomes steeper is the degree measure. So yeah, so as you increase the degree measure, your sine of that angle is going to increase as well, up until you get a straight up and down ski slope, which would be pretty dangerous, in which case your acceleration would just be 75 times 9.8 there. All right. I think those are the ones that you had listed in your email. So yeah, so hopefully you found this helpful. Again, my numbers might be a little bit different, so don't just copy down my answers directly. But again, hopefully that kind of gives you ideas to how to go about solving these. Yeah, hopefully you found this helpful. Have a lovely day, and I'll talk to you later. Bye now.